Alright, so I'm going to take a page from Mr. Thopper's book in tonight's video. Something he would do with his AP US History class at the end of the year last year was just have a PowerPoint slide with key points written, and then you would know what was important in his lecture based on the key points on the screen. So you could say, oh, he just talked about something. Is that related to one of the key points? If yes, write it down. If no, you could skip writing it down. So maybe in the margins of your note page, really quick, note these key points because these are the things I want you to take away from tonight's video. You should be able to define launch angle, draw the path of a horizontally launched projectile. I'm going to show you some new equations, and I'm going to show you how to get them out of our old equations, and so you should know how to do that because the new equations are not on the blue sheet, and there'd be no point in memorizing them if you know the old equations. And then also how to solve for a landing point with no numbers and then with numbers. So it's missing a little part there. No numbers and with numbers. Those are your key points. Just in the margins, really tiny, so you can look back and say, okay, is the thing he just talked about related to one of these? If it is, write it down. If not, maybe skip it. So first off, launch angle. Launch angle is the direction of your initial velocity with respect to the horizontal, or your angle with relationship to the x-axis if you define your x-axis to be the part where you're coming from. So notice in the example on the left, the diver is jumping and she's clearly jumping at an angle. So she has some angle other than 0. Her velocity has some angle other than 0 when she jumps. However, here our cliff jumper jumps straight out according to the velocity vector, and so she has a launch angle of 0. So launch angle is just how your initial velocity was directed when you first jumped. Next, this is the trajectory of a projectile launched horizontally. So if this was our diver over here, and she jumped straight off the cliff, she would follow the path drawn here. Notice that she has virtually no flat line here. In fact, on a perfect projectile, there is no flat line there. As soon as she jumps off that cliff, she starts falling because she has downward acceleration the whole time with magnitude 9.81 meters per second squared. So because she has that acceleration the whole time, that's what causes her to have this parabolic trajectory. Alright, equations. Let's think back to the equations we already know. So please don't panic with all the stuff on the screen at the moment. I'm going to write out the equations we've been using up to this point. So we have final velocity equals initial velocity plus acceleration times time. We have final position equals initial position plus initial velocity times time plus half acceleration times time squared. And we have v squared final velocity squared equals initial velocity squared plus 2 times the acceleration times your change in position. Now let's think about if we were to have a projectile launch straight out. So if this is our cliff and our person jumps straight out, what can we say about them? Well, in x, they have some initial velocity, so their jump gives them an initial velocity, but there is no x acceleration. Once they're off the cliff, the only thing pulling them down is gravity. They have no other acceleration. They're not pushing or pulling on anything else, so their only acceleration is gravity, which is in y. So let's take the equation x equals x naught plus v naught t plus 1/2 at squared and figure out what it looks like for both x and y. So in x, our initial position we can define to be 0 if we set the origin at the jump point. Then we can say, alright, the person jumps out, they have some velocity, so they have it. It doesn't have to be 0. We'll keep the v naught t. But then their acceleration is 0. The only thing acting on them is gravity. So acceleration is 0. And that equation reduces down to x equals v naught t. So anything launched with a 0 angle, just jumping straight out, this is their x equation for distance. Now let's do that for y. So y, their initial position in y, we can define to be 0. We can call the top of that cliff 0. Or we can say they have a certain height h. So in this case, our x0 is h, if we don't define the top to be 0. Then they have no initial y velocity if they jump straight out. So think about the question from 2 days ago when you were picking vectors with no x and no y component. If someone jumps straight off the cliff, like up at the top, that velocity has no y component, so plus 0. And then their acceleration is g, or 9.81 meters per second squared, so 1/2 gt squared, which becomes this equation. So for a 0 launch angle, the x equals x0, so forth equation turns into y equals h minus 1/2 gt squared. Mr. Melvin, do I have to memorize all the equations on this screen? No, you just have to know how to get to them, which is what I'm showing you. All right, let's look at the second equation. V equals v0 plus at. V equals v0 plus at. Well, in x, you have the initial velocity you jumped off with. So for x, vx, we do have our initial velocity, but we have no acceleration. So we get this equation right here. V final in x equals v initial in x. And then in y, for vy, we have no initial velocity if we jump straight out, no y component. And our only acceleration is g, and in this case, since down is typically negative, we would get vy equals 0 plus negative gt, which is this equation here. Next up, we know from before that our initial x velocity doesn't change, so this equation right here, of course, reduces to this one in x. And then we know in y, just like in the equation over here, just like in the equation over here on the left, the only acceleration is g, and so a becomes g. And if we define up to be positive, that's negative g. And so the v squared equation turns into this one. So all I want you to get out of this is how, given a 0 launch angle problem, you could take one of these equations and arrive at one of the others down here. That's all. Okay, next. There are going to be some problems that ask you to find how far something travels in x by the time that it lands. And this is such a common problem that you're going to be asked to answer that I'm just going to show you in general how to solve that problem. If something is launched off a cliff with certain speed of a certain height, where will it land? Give its x position where it lands. Okay, so when it lands, something that's going to be true is it's hit the ground. And let's set the ground at the origin for y. Alright, we're going to take two equations that I showed you on the last slide. Y equals h minus 1/2 gt squared, and x equals v naught t. Remember, both of those just came from x equals x naught plus v naught t plus 1/2 at squared. If you're not sure how I got these two equations, go back and watch the last 3 minutes of the video. Now my goal is to solve for x. I don't know in these equations usually a time. So I'm going to show you how to eliminate time. Remember, this is just a common problem. That's why I'm showing you how to do it kind of on its own. To eliminate time, I'm going to do that by substitution. So I'm going to take the simplest equation, which is this one, and solve it for t. To do that, I divide v naught on both sides, and I arrive at x over v naught equals t. And I'm going to take that t that I just found and plug it in for t in this equation. So the y equation becomes y equals h minus 1/2 g x over v naught squared, which then, if I multiply through the 1/2 and the g and pull out the x from the parentheses, looks like h minus g over 2 v naught squared x squared. So I carried through the exponent, the squared, and multiplied through the 1/2, the g, and pulled out the x out of parentheses, because I'm eventually solving for x. We know that when the projectile hits the ground, y is 0, so we can rewrite this equation as 0 equals h minus g over 2 v naught squared times x squared. Now we can start to solve for x. So the first thing I'm going to do is move h over, so I'll get negative h equals negative g over 2 v naught squared, all times x squared. Then, because I'm getting x by itself, I'll divide by g over 2 v naught squared. So basically I'll multiply both sides of the fraction, or both sides of the equation, by the reciprocal of that, negative 2 v naught squared over g. So I just flipped, changed to a different color. I just took this fraction and flipped it. And so it will cancel out on one side and leave me on the other side with x squared equals 2 v naught squared h over g. And then I take the square root of both sides, and once I've done that, I arrive at this equation here. That's the equation for distance of a projectile launched at a 0 angle. And if you're just like, whoa, that was a lot of math, and I'm really confused right now, we're going to work some examples, but I just wanted to show you the algebra that you have to go through when you're not given time for a projectile launched at a 0 angle. So if you're a little lost, examples are coming. Here's the next problem we're going to solve, or the first problem we're going to solve. A ball rolls off a 2-meter table with a speed of 5 meters per second. How long does it take to land, and how far from the table does it land? Alright, so first off, we know that its initial, I'm going to list my givens, we know its initial y position, y naught, is 2 meters, because it's 2 meters off the ground. Let's call the ground 0. And we know its initial x velocity, v naught x, is 5 meters per second. We also know its acceleration in y is going to be negative 9.81 meters per second squared. So by calling that negative, I've also decided that up is positive. If I didn't decide up was positive, I'd have to set my 2 meters for y naught to be negative. So I'm just setting the acceleration negatively. You could do it the other way, and you'll get the same answer that I do. First, I want to know the time it takes. So, thinking back to our position equation, rewritten for y, we have y equals y naught plus v naught y t plus 1/2 gt squared. Now I know some things. I know that my final y position on the ground will be 0. I know my initial will be 2 meters, but I'm going to leave that as a variable right now. I know that v naught y is 0, so I can eliminate those parts of the equations, and I'm left with 0 equals y naught plus 1/2 gt squared. And I'm solving for time, so let's bring this over here. Negative y naught, just moving the y naught to the other side, equals 1/2 gt squared. And then I can say negative y naught. Let's multiply by 2 to get rid of the 1/2, and divide by g. Notice I'm doing 2 steps at the same time, so this becomes negative 2y naught over g equals t squared. We know that g is actually negative, as I've defined it above, so we could just say the negative's part of g, and it's fine, it's not necessarily a mistake. But for the sake of simplicity, since people freak out with negatives, I am going to put the negative on the g, and notice that the negative and negative in the fraction will cancel out. So now I'm left with, flipping it around, t squared equals 2y naught over g. Therefore, t equals the square root of 2y0 over g. And then I plug in my numbers to find the time. Why don't you do that real fast, and I'm going to clean this up on another slide. So pause the video, plug in the numbers to find the time. Alright, so I plugged in 2 meters for y0, 9.81 meters per second squared for g, took the square root, and I got 0.64 seconds. So I've answered the first question, how long does it take to land? There's my answer to the first question. And that actually makes answering the second question pretty easy. How far from the table does it land? So I know that my position equation says x equals x0 plus v0 t plus 1/2 at squared. So my x position is what I'm trying to find. Initial x is going to be 0. I have an initial v0, 5 meters per second, so I'll leave that alone. There's no acceleration in x. The acceleration due to gravity is only in y. And so my equation reduces to x equals v0 t. I have a v0, 5 meters per second. I have a t, 0.64 seconds. Therefore, x equals 5 meters per second times 0.64 seconds. And I multiply that out. It's going to be it's going to be exactly 3.2. X equals 3.2 meters from the table. So I found the time it takes to hit the ground, and I found out, given its initial velocity, how far it is from the ground. Alright, moving on to the next example. Alright, here's our next example. A car drives off a cliff at 45 meters per second. It takes 6 seconds to reach the ground. How high is the cliff? So, I'm going to write my givens. We know the car's initial x velocity is 45 meters per second. You might be wondering, how do you know that's not y? Well, cars don't drive up and down. Cars drive left and right, unless you're in a Jason Bourne film. The time it takes the car to fall is 6 seconds. And I know I'm dealing with height, so at some point I have to have a distance come into play. And remember, I've said before my favorite equation when it comes to distance, x equals x0 plus v0 t plus 1/2 at squared. So I'm going to write out the version of that equation for y. Y equals y0 plus v0 in y times t plus 1/2 the acceleration in y times t squared. And the acceleration in y is g, and it's negative, so I can rewrite this equation. Y equals y0 plus v0 in y minus, because g is negative, 1/2 gt squared. Now let's see if there's anything I can get rid of. The car is going to hit the ground, which means that its final y position is 0. Let's set the origin at the ground, so down here is my origin. y0 is what I'm looking for. I can't eliminate that. I want to know how high it started out. It has no initial y velocity. All of its velocity is in x, so that's 0. And we already said acceleration is g. So now let's just rewrite the equation with what we have left. I'm also going to move it over here to the left a bit, so bringing it over here. 0 for final position equals y0 minus 1/2 gt squared. So notice this term went away and this term went away. There was a t here at some point, not really sure what happened to that t, where it went, but luckily it's in a term that went away. So now I'm down to this equation, 0 equals y0 minus 1/2 gt squared. Now I'm going to rearrange that equation slightly, bring the negative 1/2 gt squared over to the other side. It will become positive because you have to add it to get rid of it. Gt squared equals y0. And look, the equation's done. I was trying to find y0, and I have the equation ready for that. So now I just plug in g, which is 9.81 meters per second squared. Plug in my time, which is 6 seconds. Square that, so let me grab the calculator. And I will do 1/2 times 9.81 meters per second squared times 6 seconds squared. And I get the cliff was 176.58 meters. That seems pretty crazy, although it could definitely be true. You might want to check my math on all that. Let me know tomorrow if I was wrong, but 6 seconds is a long time to fall, so I could definitely believe the car was that high. Alright, notice at the end of my problem I checked the reasonability of my answer. I said, does that seem right? 6 seconds is a long time to fall, so sure, I could believe something falls, let's see, 600 feet in 6 seconds. That makes sense. But I also said that's awfully big. Someone ought to check me. This problem is all in terms of variables, which is something you need to get used to, solving with variables instead of numbers. Why don't you try this problem, pause the video, and come back for the correct answer. First off, I've identified my givens. Y naught is h, final x position is L, and I'm trying to find initial x velocity. If you had trouble there, why don't you pause the video again and try it now, and then come back for more. Next up, I took the position equation, x equals x naught plus v naught t plus 1/2 at squared, and I reduced it down to this. X is v naught x, times t, and y is h minus 1/2 gt squared. Look at the kinematic equations on the blue sheet, the first 3 equations. Try to figure out how I got there. If you're not sure, scroll back to earlier in the video where I talked about solving for something that doesn't give you time, because I talked about how to get these equations. And, what a perfect example, this problem does not give you time. So see if you can figure out how to deal with the problem of not having time. Pause the video if you haven't gotten that far, and try it in the problem. Then come back for the answer. Okay, so I'm going to take this equation here for x, and remember, I'm ultimately trying to get v naught x. What I don't have is a time, so I have to get rid of the t. To do that, I'll solve the x equation for t. And just divide by v naught x. X over v naught x equals t. And now I can plug that into the other equation. So plugging that into the y equation, y equals h minus 1/2 g x over v naught x all squared. Alright, now I solve for v naught x. Not necessarily the easiest thing in the world to do, but I do it. If you had trouble getting this far, why don't you try solving for v naught x now? Pause the problem, come back for more. Alright, now I'm solving for v naught x. Let's go ahead and square everything in that parentheses. So I have y equals h minus 1/2 g x squared over v naught x squared. Whew, this is going to be a tough one. So now, let's move the h over. Y minus h equals 1/2 g x squared, negative 1/2, I dropped my negative, over v naught x squared. Now I'm going to multiply by 2 and divide by g. So let's do that step. 2 y minus h over g equals x squared over v naught x squared. And that becomes, if I divide by x squared, 2y minus h over g x squared equals 1 over v naught x squared. See if you can figure out how to deal with the fact that we just got what we're looking for in the bottom of a fraction. I'll do it on the next slide, but maybe you should try it on your own first. Here's where I am. First thing I'm going to do is invert both sides of the equation. Yes, you can just do that. It's called raising the whole thing to the negative first power. So I'm going to raise the whole thing to the negative first power, which just flips both sides. Now I have gx squared over 2y minus h equals v naught x squared. Alright, now take the square root of both sides, and we get, I'm going to flip it around, I like my unknown being on the left, v naught x equals the square root g x squared over 2y minus h. And the last thing to do, which I really should have done earlier, that x the problem gives as L, so I wrote down on the last slide, x equals L. So let's rewrite it for our final answer. V naught x equals the square root of g L squared over 2 y minus h. And I wonder if the problem gave me y. Let me look back at that problem. Oh, it hits the ground. Now I feel like a dummy. Okay, so y goes away. Remember, if we hit the ground, our final y position is 0. So I made a mistake, but it's easily fixable. Let's just put that in. And since I'm treating the ground as 0, my acceleration really should be negative g. Again, we could say the negative is just contained in g, but it doesn't hurt anything to say g is positive 9.81 meters per second squared, and then use negative g in your equation. So this equation reduces down even further when I get rid of that pesky y to v naught x equals the square root of negative gl squared over negative 2h. Alright, hopefully my not including the negative on g didn't throw anybody off too much, but that's how you solve this problem. And you'll have lots of practice with this tomorrow in class. Also, there are problems in the extra practice on the website, just like always. Big shout out to Gabby and Edgar for doing the extra practice problems, and Gabby for coming to get help with them on the post 2 nights ago. Great job, guys and gal. Keep it up, and more people should be doing it. That's all for tonight.